2.5 lesson 1, limits involving infinity. Our objectives for today are 1. For a given function f, you'll be able to determine the limit of the function as x approaches infinity, which is called a limit at infinity. Because we're taking the limit of the function as x is approaching infinity, we call that a limit at infinity. And then objective 2, you will be able to determine when an infinite limit arises. Now that's different because in the first case, it is the input value that's approaching infinity. In the second case, the input value is approaching a particular number represented here by c. For example, x could be approaching 2, x could be approaching 5. And then the output values are going to infinity or negative infinity. We call that an infinite limit. So you'll be able to determine when an infinite limit arises. So that's objective 2. In objective 1, it is the input that is approaching infinity, and we call that a limit at infinity. For objective 1, the input could also be approaching negative infinity. For objective 2, the output could also be approaching negative infinity. Objective 3, you'll be able to find the limit of a rational function at infinity. So at infinity means, again, like objective 1, the input values are going to infinity. What's a rational function? It's a ratio of polynomial functions. So you'll have a polynomial function in the numerator, and then you'll have another polynomial function in the denominator, and that makes a rational function. So for objective 3, what is a rational function? A rational function is a ratio of two polynomial functions, but the denominator is not 0, and here is an example. So we have a ratio of two polynomial functions, one in the numerator and one in the denominator. Now we will take a look at objective 1. For a given function f, you will be able to determine a limit at infinity. So what happens as the input values go to infinity for a given function f? That's called a limit at infinity. So we look at our first example here. Our function is f of x, and it is equal to 1 over x minus 2 squared plus 3. And we want to know the limit of this function as the input values go to infinity. This is called a limit at infinity. So what happens to the output values as x gets larger and larger and larger? So you can try values for x like 12, 102, 1002, because they're easy to work with. When, for example, x is 12, then you have 12 minus 2 is 10. 10 squared is 100. 1 divided by 100 is 0.01. And plus 3 is 3.01. So I'm making a table of x and y. So if I choose x to be 12, then 12 minus 2 is 10. 10 squared is 100. 1 divided by 100 is 0.01. Plus 3 is 3.01. If I choose x to be 102, then you have 102 for x, minus 2 is 100. 100 squared is 10,000. 1 divided by 10,000 is 0.00001, plus 3 is 3.00001. And then you have x would be, you can try 1,002. Minus 2 is 1,000. 1,000 squared is, I believe, a millionth. A millionth plus 3 would be 3.0000001, something like that. But you can see that as the input values are getting larger and larger, as the input values go to infinity, you can see that the output values are getting closer and closer to a particular number, 3. So we say the limit at infinity for f of x is 3. So these are the correct values for the table. Looks like I had one extra 0 here that I shouldn't have had, and the same thing can be said for the next row. I had an extra 0 that I shouldn't have had. But the idea still remains the same. As the input values go to infinity, the output values approach 3. So the limit at infinity for this function f of x is 3. So we have the table, we know the limit, and look at the graph of the function f. You can see what's going on as the input values get larger and larger. the output values get closer and closer to 3. So there is what we call a horizontal asymptote, and the horizontal asymptote is the line y is equal to 3. So the output values of the function get closer and closer to 3 as the input values approach infinity, and the graph has what we call a horizontal asymptote. Now consider what happens as the input values approach negative infinity. Well, I can make a table here, x and y, and I would like to choose values for x that would make it easy for me to do the calculations for the function f. So for example, if I choose x to be negative 8, negative 8 minus 2 is negative 10. Negative 10 squared is 100. 1 divided by 100 is 0.01, plus 3 is 3.01. And if I choose x to be negative 98, you'll have negative 98 minus 2, which is a negative 100, and if you square that, you get negative 10,000, and then you're going to add that, you're going to do 1 divided by, if you square that, you get positive 10,000. A negative times a negative is a positive, and then 1 divided by 10,000 is 1/10,000th, and add 3 to that and you get 3.0001. And if you choose x to be negative 998, negative 998 minus 2 is negative 1,000, and negative 1,000 squared is a million, and 1 divided by a million is a millionth, plus 3 would be 3.000001. So this is also a limit at negative infinity. So as x approaches negative infinity, you can see that the x values are becoming more and more negative. You can see what's going on with the y values. They're getting closer and closer to 3. So that's what we have. We have this limit at negative infinity being equal to 3. So again, this is called a limit at infinity, or you can say a limit at negative infinity. Either way, it's okay. Just say limit at infinity. Either x is approaching positive infinity or negative infinity. And the limit at infinity, well, we can say the limit at positive infinity is 3. The limit at negative infinity is also 3. So it's probably good to distinguish between positive infinity and negative infinity, just because for some problems they could actually be different. So this was the table that I had shown you earlier. As the input values approach negative infinity, the output values are approaching positive 3. And graphically, that gives you this limit here. This limit at negative infinity gives you a horizontal asymptote. And the horizontal asymptote is the line, y is equal to 3. You can see that as the input values get close, as the input values approach negative infinity, the output values are approaching 3. So the graph has a horizontal asymptote. The line y is equal to 3. So we just looked at two limits at infinity, and now we're going to look at an infinite limit. So in an infinite limit, it is the limit that's going to be, the limit will not exist. So let me be clear about that. But we want to specify the way in which it fails to exist. We say the limit does not exist because the output values are not going to be approaching a particular number. They'll be increasing or decreasing without bound. So the limit does not exist, but we can be more specific than that. We can say, here's how the limit fails to exist. The output values are going to infinity or negative infinity. And this is called an infinite limit. So the input values are approaching a particular number. The output values are approaching either infinity or negative infinity. So because the input values are approaching 2, you want to try like 1.9, 1.99, 1.999, and then 2.001, 0, 1, and 2.1. So you can see that the input values are approaching 2 from the left of 2 as well as from the right of 2. And we want to know what's going on with the output values when that's going on, when that's happening with the input values. Now these are easy numbers to work with. You can substitute for x and subtract 2. You get negative 1/10 in the first case. You get negative 100th, negative 1,000th. You can square it, and then you can do 1 divided by that and add 3 to see what you get here. Of course, you could just enter this into Desmos, and it would do it for you. And you can see what's going on here. As the input values get closer and closer to 2 from the left of 2, the output values are getting larger and larger. They're increasing without bound. So the limit does not exist because the output values are not approaching a particular number. However, we can be more specific than that and state the way in which the limit fails to exist. We can say that as the input values approach 2 from the left of 2, so for this particular part of the table, we're actually just looking at the limit of the function as x approaches 2 from the left of 2, and it is going to infinity. And for the second part of the table here, as the input values approach 2 from values that are greater than 2, we see the same thing going on. The output values are approaching infinity. They're getting larger and larger. So we have the limit of f of x as x approaches 2 from the right of 2 is also infinity, which means the limit does not exist because it's not the output values are not approaching a particular number. And because, but we can be specific and specify the way in which the limit fails to exist. The output values are increasing without bound, whether x is approaching 2 from the left of 2 or x is approaching 2 from the right of 2. So it makes no difference whether x is approaching 2 from the left or the right. So the two-sided limit as x approaches 2 from either side also does not exist, and it fails to exist because the output values go to infinity. So this is an example of an infinite limit. So as we just saw, you can consider an infinite limit as x is approaching a particular constant either from the left or from the right or from both directions. And you could also have the output values approach negative infinity for any one of these considerations where x is approaching a constant from the left or from the right or possibly from both sides. So you could also have negative infinity, and that would also be considered an infinite limit. So graphically, what does this infinite limit tell us? It tells us that as the input values get closer and closer to 2, the output values increase without bound. So graphically, at x is equal to 2, there is what we call a vertical asymptote for the graph. Now, first of all, you've got to understand that x can never be 2, because if x were equal to 2, the function would be undefined, because you would have division by 0, which is undefined, and you see that in the table. But as the input values get closer and closer to 2, either from the left of 2 or from the right of 2, the output values just increase without bound, so the graph has a vertical asymptote at x is equal to 2. So in the first two cases, we had limits at infinity, and the limits at infinity gave us a horizontal asymptote for the graph, and the horizontal asymptote was the line y is equal to 3. And in the third case, we had an infinite limit, and the graph gave us a vertical asymptote at x is equal to 2. So what did we just do? We looked at objectives 1 and 2. For a given function f, you will be able to determine a limit at infinity. So the input values are approaching infinity or negative infinity. That's called a limit at infinity or negative infinity. And then we looked at objective 2, where you were looking at an infinite limit. The input values are approaching a particular number, such as 2, and the output values are going to infinity or negative infinity. That's called an infinite limit. And you could also consider what happens as the input values approach C from either the left of C or the right of C. And now we're going to take a look at objective 3. You'll be able to find the limit of a rational function at infinity. So it's like objective 1, in which the input values are approaching infinity or negative infinity, and we want to see what's going on with the output values. So let's look at, you'll be able to find the limit of a rational function at infinity. So as we saw at the beginning of our lesson, when we were going over the objectives and the vocabulary, a rational function is a ratio of two polynomial functions, but the denominator is not 0, and here's an example. So we want to know how to find the limit of a rational function as the input values go to infinity. That's called the limit of a rational function at infinity. So here's our first example. Our rational function is 2x plus 5 divided by 3x squared plus 1. And we want to find the limit of this rational function at infinity, meaning the input values are approaching infinity. So here's one way you can work with this. And we may be able to generalize after we look at our 3 examples. And in fact, there is a very easy way to work with this. But before we look at generalizations, let's look at how we can deal with this one at a time first. So x is approaching infinity. So basically, we want to know what's going to happen with the output values of the function as the input values get larger and larger and larger. One thing you can do is you can manipulate this function algebraically to have an idea of what might happen. And we know that whenever we multiply a function by 1, we don't change it. So we're going to multiply our rational function by a form of 1. And the form of 1 that we will choose to work with is, we look at the highest degree term in the denominator, which is x squared, and we're going to multiply the numerator and the denominator by 1 over x squared. And what happens when we do that? We're going to have the following. We have the limit as x goes to infinity, and multiply the two terms in the numerator by 1 over x squared. So when you do that, you get 2x over x squared plus 5 over x squared. And in the denominator, do the same thing. Multiply these two terms by 1 over x squared. And when you do that, you get 3x squared over x squared plus 1 over x squared. So what happens here? Well, you can cancel the common factor of x that you have in the numerator and the denominator for this particular term, and that will give you 2 over x. And you can cancel the x squared that you have here in the numerator and the denominator, and that would just give you 3. So now we look at what we have here, and we're trying to understand what's going on with each of these terms as x approaches infinity. Well, as x goes to infinity, if you have x in the denominator, as you have here, and the denominator is getting larger and larger and larger, divide 2 by larger and larger denominators. The quantity 2 over x will approach 0. And divide 5 by larger and larger denominators. The quantity 5 over x squared will approach 0. Nothing happens to 3. 3 is just a constant. There's no x there, so 3 is not affected. It stays 3. 1 over x squared, as x gets larger and larger, will go to 0. So what happens is this. The numerator will go to 0, and the denominator will go to 3, so the limit will be 0. So the limit of f of x as x approaches infinity is equal to 0. So we can write here the limit of f of x as x approaches infinity is equal to 0. Let's look at example B. But before we look at example B, we will make a note about the graph of this rational function. Because the limit at infinity is 0, the graph will have a horizontal asymptote, and the horizontal asymptote will be the line y is equal to 0. And you can verify by looking at the graph of this function. So here's our second example, and like our first example, we have a rational function, and we want to find the limit of this rational function at infinity. So like we did for our first example, we'd like to go ahead and algebraically manipulate our rational function by multiplying by a form of 1. And just like we did for our first example, we look at the highest degree term in the denominator, which is x squared, and we're going to multiply the numerator and the denominator by 1 over x squared. And of course, that's a form of 1, so you don't change your function. But look at what happens here. As x goes to infinity, now our function will be rewritten as follows. When you multiply 2x squared and 5 by 1 over x squared, you will get 2x squared over x squared plus 5 over x squared. And then in the denominator, when you multiply 3x squared and 1 by 1 over x squared, you will get 3x squared over x squared plus 1 over x squared. So now you have something that's equivalent to the original function, f of x, but you can now cancel the common factors of x squared in that first term, so that will just leave you with 2. And you can now cancel the common factors of x squared in this term, and that will just leave you with 3. So what happens as x goes to infinity? Well, nothing happens to 2, nothing happens to 3, but as x goes to infinity, 5 over x squared will go to 0, because the numerator is always going to be 5, but the denominator is going to be getting larger and larger. So when you divide by larger and larger denominators, the quotient will approach 0. And by the same reasoning, 1 over x squared will go to 0. So what's our limit here? It'll be 2 plus 0 divided by 3 plus 0, or 2/3. So the limit at infinity for this function f of x is 2/3. So before we go on to our next example, if you were to graph the function f of x, because of this limit at infinity, you will see that the graph has a horizontal asymptote, and the horizontal asymptote would be the line y is equal to 2/3. So now we take a look at example C, and we have our function f of x, and we want to find the limit at infinity of this rational function. This is a rational function, and we're finding a limit at infinity. And like we did for our previous two examples, we're going to multiply our rational function by a form of 1 to help us find this limit at infinity. And we're going to multiply it by this form of 1. Again, just like we did in the previous examples, we look at the highest degree term in the denominator, which is second degree. So we're going to multiply the numerator by 1 over x squared and the denominator by 1 over x squared. So we're multiplying by a form of 1. And when we do that, this is what we have. We have the limit as x goes to infinity of, so you have 2x cubed plus 5, multiply each term by 1 over x squared, and that will give you 2x cubed over x squared, and then you will have plus 5 over x squared. And then in the denominator, multiply 3x squared by 1 over x squared, and then multiply 1 by 1 over x squared. And when you do that, you get 3x squared over x squared plus 1 over x squared. So now you can do some simplification. So you have x cubed divided by x squared. So when you cancel common factors, that will just leave you with 2x. And in the denominator, you have x squared divided by x squared. So when you cancel the common factors, you will just be left with 3. And what's going on here as x approaches infinity? Well, as x goes to infinity, 5 over x squared will go to 0. And 1 over x squared will also go to 0. Because in both of these, the numerators are constants. As the denominators get larger and larger, the quotients will approach 0. 3 is not affected because it's just a constant, but look at this one here, 2x. As x gets larger and larger, 2 times x will also get larger and larger. So this goes to infinity. So what we have here for the limit is infinity plus 0 over 3 plus 0. Basically, what that tells you is that as x goes to infinity, the output values from the function f will also go to infinity. So here we have an infinite limit at infinity. So we have the limit of the rational function f of x as x approaches infinity, which is a limit at infinity. In this particular case, this limit at infinity also happens to be infinity. So this is called an infinite limit at infinity. You don't need to write infinity divided by 3, you just write infinity. So graphically, this will tell you that the end behavior of the function f of x as your input value, as you look to the right, x is approaching infinity, so you're looking towards the right on the graph. The y values are increasing without bound. So that tells you about the end behavior of the graph of the function f. So let's take a look at the 3 examples that we just did and see if we can come up with some generalizations. In the first case, our limit was equal to 0, and in the second case, our limit was equal to 2/3, and in the third example, our limit was equal to infinity. There is an easy way you can remember how you will get the limit of a rational function at infinity. You can compare the degree of the numerator to the degree of the denominator. If the degree of the numerator is the same as the degree of the denominator, then the limit of the rational function at infinity would be equal to the quotient of the leading coefficients. On the other hand, if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function at infinity would be equal to 0. And finally, if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function at infinity would be infinity. For this third one here, we will just say the limit does not exist. For this particular problem, it would fail to exist in this particular manner because the leading coefficients have the same sign. If they had opposite signs, then this would be negative infinity. And here we just have the guidelines that I just said verbally, written out. If the degree of the numerator is less than the degree of the denominator, then the limit of the rational function at infinity is 0, as we see here for example A. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function at infinity is the ratio of the leading coefficients, as we saw here for example B. And if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. And in this particular case, the limit, this is the manner in which the limit fails to exist, as we saw here in example C. And as a note, I have included here the graphical interpretation of each of these limits. The first two will give us horizontal asymptotes of the graph of f, and the last one, for example C, will give us end behavior of the graph. You can verify by graphing each of the rational functions and seeing for yourself. So today we looked at these 3 objectives. In the first objective, we looked at how to find limits at infinity when the input values were approaching infinity. And in the second objective, we looked at how to find infinite limits. The input value was approaching a particular number, and the output values were going to infinity or negative infinity. So those are called infinite limits. And in the third objective, we looked at how to find the limit of a rational function at infinity.